Okay, let's look at some more examples of evaluating limits algebraically or analytically. Sometimes we're going to have equations or functions that we can't necessarily factor, so we're going to need other techniques to evaluate them. In this case, this example has a radical, and for radicals you're going to want to use a technique called rationalization. You may remember from before, from pre-calculus or algebra 2, that we can get rid of this radical of the square root of x plus 1 if we multiply this square root of x plus 1 minus 2 by its conjugate. Remember, conjugates are special because for conjugates, when we FOIL them out, the outside and the inner terms cancel. The middle terms cancel out and disappear. So we only have to multiply first and last terms together. And then because this involves a radical, when we multiply the first terms that have radicals, it also makes the radical go away. So we're going to multiply by the conjugate on the top, and then we need to do that to the bottom as well. Now remember, with conjugates, the only thing different is this term that's here in the middle. Okay, so now let's see what happens. The limit as x goes to 3, and remember I'm doing this because if I plug 3 into the bottom, I get a 0 in the denominator, so I've got to come up with some way to clean this up. As I FOIL the top, the square root of x plus 1 times the square root of x plus 1 is just x plus 1. And negative 2 times positive 2 is negative 4. So that cleaned that numerator up drastically. All right, now in the denominator, I'm going to leave my factor of x minus 3 and my factor of the square root of x plus 1 plus 2. I'm not going to FOIL that out because remember, the whole idea is to factor things so that things will cancel. So we need to leave the denominator in its factored form. Now I'm going to collect like terms up here. This plus 1 and minus 4 can combine. So that's going to give me x minus 3. And look how convenient. I have an x minus 3 in the denominator. So this is going to work out for me, and I'll be able to cancel the x minus 3's. Now, that got rid of what was giving me the 0 in the denominator. There's obviously a hole in the graph at 3 since those factors canceled. And now I'm going to plug in 3 for every x. The numerator is 1. And when I plug 3 into the bottom, I'm going to plug this 3 right here in for the x. That's going to give me the square root of 4, which is 2, plus the other 2 is 4. So my limit is 1/4. And here's the graph of this equation. You can see at 3, the hole is at about 1/4. So that works out. Okay, let's look at a few more examples. I'm going to skip ahead to this piecewise function here. When the function is a piecewise function, you have to be careful because we're wanting the limit at -2. So we really want to answer this part C. But since this piecewise function splits off at -2, the key here of what's of importance to us is, do these two pieces come together at -2 or do they have different y values? So you always have to check both sides in a piecewise function. Now, the first one, part A, is approaching -2 from the left. Well, since the top piece is x is less than -2, less than would be to the left of -2. So technically, to evaluate part A, to evaluate -2 from the left, I need to use the top piece, which is the quadratic. Now, just because it's coming from the left, remember we can still plug in -2. So I'm going to plug -2 in for every x and evaluate. So that's going to give me 2. Okay, now -2 from the right will be all values greater than -2, so we're going to use the piece on the bottom. I'm going to directly substitute -2. That's going to be -1/2 times -2 plus 1, and that's also going to give me 2. Well, since the left-hand limit and the right-hand limit are the same, then I'm safe to say that the answer to part C is 2. Notice in this piecewise function, x is never equal to -2. So in this piecewise function, g of x, g of negative 2 does not exist, but since there's a hole and these two pieces are coming together at the hole, the limit does exist. So anytime you're given a piecewise function, if you're evaluating for the x that splits the pieces, then you should always evaluate both sides and compare. Okay, now let's take a look at a few more examples. There are several examples in these notes, and I did go through every example in class. So whatever examples I do not cover in this video, you are welcome to try them on your own and then check your answers against the OneNote file that I've posted in It's Learning. All right, so let's scroll through and let's just pick a few to try. I'm not going to do many here at the beginning because, again, remember it's just direct substitution. So you're going to plug the value for x straight into the function and clean up. Now, sometimes Part A does give students a little trouble because they see E and it makes them panic. But remember, E is just a number. And so when I plug this in, I will get natural log of E, replacing x, and 2 times E. E is just like pi. It's one of those special numbers. So this is a complete answer. However, we should recognize that the natural log of E is equivalent to 1. And then 2e would be some decimal. I'm just going to leave it 2e. And 1 over 2e will be my final answer. Now remember, natural log of E, the base is understood to be e. So we're saying e raised to what gives me e. And so that would have to be 1. Anytime the base and that number are the same, it equals 1. I'm not going to go over b because you're going to just plug 5 straight into the equation. Same thing with c. I would like to emphasize that sine of pi quantity squared is the same thing as sine squared pi. So technically you have to evaluate sine of pi and then square it. And so then we'll plug in pi for the other theta. We should use our unit circle to clean this up. Sine of pi is 0, so this is going to give me 0, plus 2. Cosine of pi is -1, so my final answer is -2. Okay, so let me just skip ahead. I'm going to try to do 1 or 2 more that are a little more difficult. Make sure in Part D you know your unit circle. You can clean that up. Part E, when I directly plug in -2, it's going to give me a 0 in the denominator. So for this one, I am going to need to factor and see if that will help me. So the top factors as x minus 3, x plus 2. Remember, you're looking for 2 numbers that will multiply to give you -6 and add to give you -1. In the denominator, I can factor out a GCF of 2. And so that works to my advantage. Now these x plus 2's cancel, and the fact that I had a -2 in the 0, a -2 made 0 in the denominator, that's solved now. The factor is canceled out. There's a hole at -2, but the limit still exists because when I plug -2 into the numerator now, I get -5, and then I still have a 2 in the bottom. So the limit is actually -5 over 2. So don't forget what that means. There's a hole at -2 in this graph, but the graph is coming together at the hole. Okay. Let's try 1 or 2 more. Look what happens with f. Okay, when I plug 3 into the function on the denominator, I get a 0 in the bottom. So I'm going to try to factor. I can factor the denominator as the difference of 2 squares. But it didn't help. When I plug 3 into the bottom, I still have a 0 in the bottom. So I know there's a vertical asymptote at x equals 3 because it makes the denominator 0 and I can't get rid of it. And because I can't get rid of it and factoring didn't help, direct substitution is not going to work because there is a break in the graph at 3. So I'm going to say this limit does not exist. Okay. Part G, I'm not going to take time to go over, but you do need to recognize that this is the difference of two cubes. So you're going to factor this one, but you'll need to remember the factoring pattern for the difference of two cubes. I'm going to skip H and I. Here for H and for I, you would use the conjugate method. So you have an example like that I've already gone over. So I'm going to skip ahead to for J, we need to get a common denominator here. All right, so we need to get a common denominator. For K, you can try to factor and reduce. And then let me go back. I want to go right back to the very last ones. For L and for M. Okay, so on these last two examples, if we try to directly substitute 3, it's going to give us a 0 in the denominator, and we cannot factor or simplify that. It won't go away. So these are the two problems where we have to test values. Okay, so a number immediately to the right of 3 would be 3.1. So I'm going to plug 3.1 into the top. 2 times 3.1 plus 5, that's going to produce a positive value. And if I plug 3.1 into the bottom, I'm going to get another positive value. So I'm going to say this limit is infinity. I know there's a vertical asymptote at x equals 3 because I can't get that 0 out of the denominator. But since it's one-sided, I'm going to plug values in to get a more descriptive answer such as infinity. Same thing over here. In this case, I want a number just to the left of 3, so I'm going to pick 2.9. So I'm going to plug 2.9 into the top. It's going to produce a positive. But in the denominator, a 2.9 minus 3 is going to produce a negative. So I will say this limit's negative infinity. Okay, so I didn't go over every example in these notes, but hopefully if you missed this lesson or you're just watching to relearn a few things, hopefully this will be enough, and then you can also go to my OneNote link file and you can see every example work. So if you try some of the other ones on your own, you can check your answers. Thanks.